Hello all. Today in this lecture, today I am going to teach you the IIR filter designing. IIR filter designing filters we are learning as a part of the digital filter designing in the digital signal processing subject. Before going to this, let me introduce what are the digital filters we have in the DSP. There are two types of digital filters. One is the FIR filter and another one is the IIR filters. And these two are classified based upon the impulse response of the filter. So if the impulse response is infinite, then we are calling it as a infinite impulse response filter. And if the impulse response is finite, then we are calling it as a FIR filters. So actually basically you can see your filter as a system. So if the system response is infinite for the input impulse, then it is called as infinite impulse response system. And if the input is finite for your given impulse, then it is called as the finite impulse response system. This is in technical way. If you want to understand the better way, you can see that, for example, infinite impulse response means you are giving the impulse as an input and it is going to produce its response continuously, infinitely. Okay, so such type of systems are called as infinite impulse response. So how come it is possible? This is possible because of the feedback or the feedback provided. So if you are giving the one shot of impulse response, this will be the given us feedback to the system. The system is producing the continuous output even though the input is absent. So this infinite impulse response means, in shortcut, the system is producing the output for a one shot of input continuously, infinitely. That's why it is called as infinite impulse response. So here we are seeing your filter as a system. So based upon that response, you are classifying the filters as two types: infinite impulse response and the finite impulse response. Okay, now so this is the basic information about the IIR filters and the FIR filters. Now in this class I am going to teach you what are the methods for designing the IIR filters. As we know that IIR filters and the FIR filters are the digital filters. Okay, the digital filters are designed using the indirect method only. We will not design the IIR filters directly because these are digital filters. They are designed indirect method. Okay, in indirect method what we are doing is we are designing the filter. We will design the filter in the analog domain only. After that, if you design the filter in the analog domain, then we are converting the filter into the digital domain, from the analog domain to the digital domain. Okay, as I said, the digital filters are designed using the indirect method. So let us see what are the designing steps and how we are going to design the digital filters from the analog filters. So I want to say you, first of all, to design the digital filter from the analog filters, first of all we have to map the desired digital frequency filter specifications to those for an analog equivalent analog filter. First of all, you have to map the desired filter specification with the analog filter. Then you have to derive the transfer function in the analog domain. Then you have to convert the transfer function of the analog filter into the digital domain. So in shortcut, I am telling you guys, listen. There are three steps, important steps for converting your analog filter transfer function into the digital filter. One thing is you have to map the specifications of the required filter with the analog filter, and second point is you have to derive the transfer function of the analog filter and you have to convert the transfer function of the analog filter into the digital filter. So let me tell you what is the purpose of deriving the analog transfer function. I told you that the digital filters are not designed directly. Designing of the digital filter is nothing but deriving the transfer function of the filter. So this is the important point you have to note down, is designing of the filter is nothing but deriving the transfer function of the filter. So because the transfer function is the representation of the filter. So you are designed the filter means you have derived the transfer function of the filter. That's why whenever we are talking about the designing of the filter, it means that mathematically we are deriving the transfer function of the filter. So keep it in your mind. So indirect method of designing the filters are nothing but indirect means we are designing the transfer function of the analog filter. It means that designing the filter in the analog domain, then after that converting the analog filter into the digital filter, right? So this is the important point you have to note down. So for example, for better understanding of the filters, let us take the low pass filter and its magnitude response. So this is the low pass filter. You can design any of the filter analog domain. Either you can design the low pass filter, or you can design the high pass filter, or you can design the band pass filter and the band reject filters. For starting purpose, we are taking the low pass filter. So we are showing you the magnitude response of the digital filter. See the magnitude response of the digital filters, pictorially both are looking like same. So I want to analyze this. So h of j omega, see this here, this omega is nothing but representation of the angular frequency. It means that this is the analog filter and this is in the analog domain, and here h of e power j omega, it means it has been converted into the digital domain. So that's why we are representing the h of e power j omega. Orally we can say this is the analog filter, orally we can say this is the digital filter, but mathematically how to show that? So this is the representation j omega, this omega is nothing but the angular frequency and this omega is nothing but the digital frequency. In this way I am going to show you the difference of the analog filter and the digital filter. The response will be same. See here, so this is the low pass filter response. So it means here, see, if you understand the designing of the filters in a better way, you have to know how to read the magnitude response. See here, how I can say it as a low pass filter means, see here, the response, you are calling it as a magnitude response, right? So the response is maximum at what? Low frequency. At what? Low frequency. At the low frequencies the response is maximum. As you are increasing the frequencies, the response is going to decrease, right? So it means that at the low frequencies you are getting the maximum output. As the frequency increases, you are getting the low frequency. It means that I can say that this is allowing the low frequencies, that's where you are getting the output, right? So this is the low pass filter in that scenario. Same way, okay. Now here in the band where you are getting the maximum magnitude response, you are calling it as a pass band, okay. PV I am representing here, pass band, and from here to here the output is decreasing from maximum to the minimum. So it means that I can say that the output is transition from higher to the lower. From here to here it is transition, right? So this band is called as transition band. From here to here almost it is going to decrease. These are the ripples. So from here it is called as stop band. So the entire region I'm converting, I'm splitting into pass band region and the transition band region and the stop band region. So now here I want to introduce, now 1 by root 2 is the 3 dB frequency. So omega p is nothing but the pass band frequency, omega c is nothing but the cutoff frequency, omega s is nothing but the stop band frequency. So the same will be applicable to here also, because this is the same response. The response will be same, only the representation is different. So here you are representing entire thing into the digital. So this is the pass band frequency in digital, omega p, and this is the stop band frequency in digital, omega s, omega c cutoff frequency, and omega s is the stop band frequency. And this is this point is maximum response. I'm indicating as a 1 plus epsilon square, and maximum allowable in pass band. So alpha, epsilon and lambda are the two parameters I'm indicating. The epsilon is nothing but the parameter specifying the allowable pass band, and the lambda is nothing but the parameter specifying allowable pass band. So this is the how to read the response. So here I have introduced only these things. Omega p is equal to pass band frequency in radians, omega s is equal to stop band frequency in radians, omega c is 3 dB cutoff frequency, epsilon and lambda are the parameters specifying allowable pass band and the stop band. Now So this is how to read the graph or response of the system. Now, after learning all these things, let us see what are the filter designing methods for designing the filter in the analog domain. I told you that the digital are designed through the analog domain. It means that if you want to design a digital filter, or if you want to design a filter in digital, you have to design that filter in the analog domain. Then you have to convert that analog filter into the digital domain, right? So it means that as a first point,